Welcome to Decoding Complexities. I am Pradeep. A system of linear equations is a set of constraints. Our goal is to find the unique values for x and y that satisfies all constraints simultaneously. There are two primary ways to represent this problem for computation. One, the augmented matrix, and the other, matrix equation. The augmented matrix combines the coefficients and the constant outcomes into a single structure. It's the foundation for procedural step-by-step solutions. The matrix equation Ax equal to b separates the coefficients a, the variables x, and the outcomes b. This is the foundation for high-level conceptual solutions. In this video, we will solve this system using both methods, starting with the fundamental algorithm Gaussian elimination. Gaussian elimination is the algorithm we use to transform our augmented matrix into a state where the solution is obvious. This target state is called Reduced Row Echelon Form, or RREF. To get to RREF, the left side of the matrix must satisfy three conditions. First, the first non-zero entry in each row, called the pivot, must be 1. And second, each pivot must be to the right of the pivot in the row above it. And the third, the pivot must only be the non-zero entry in its column. We achieve this using three elementary row operations. The first one is row swapping, meaning the two rows in a matrix can be swapped. And the second one is row scaling, which means a row in a matrix can be scaled by using a scalar. And the third one is row addition, meaning two rows in a matrix can be added together. Now let's execute the algorithm. Our target is for a pivot in row 1 and column 1. And the operation that we would be doing is to swap the row 1 and row 2. And our target is to make the value below the pivot to 0. And the operation we do here is that row 2 minus 2 times row 1. And the next target is pivot in row 2 and column 2. And the operation we do is the multiplying row 2 by the scalar 1 divided by 3. And the next target is to make the element above the pivot to 0. And the operation we do here is to add row 1 with row 2. We have reached reduced row echelon form. This matrix directly translates to x equal to 1 and y equal to 2. This algorithm is the fundamental procedural way to find the solution. Now, for the second approach, using the Ax equal to b form, we can solve this with a higher level concept, the matrix inverse. By pre-multiplying both sides by the inverse of A, we isolate X. The product of a matrix and its inverse is the identity matrix, which acts like the number 1, leaving us with the direct solution X equal to A inverse into B. This is an elegant abstraction, but it comes with a critical engineering footnote. This method only works if the inverse of A exists. That is, if A is a non-singular matrix with a non-zero determinant. If the system has no solution or infinite solutions, this method will fail. The Gaussian elimination, however, will always work and will correctly identify these cases. This is why underlying numerical libraries often use methods derived from it, like LU decomposition for robust production-grade solvers. Let's see both in code. In Python, using NumPy, we can solve this with a high-level abstraction. We can directly calculate the inverse and multiply, which gives us the correct answer. However, NumPy's linear algebra solve function is the preferred method. It is a more robust, faster, and numerically stable solver that doesn't explicitly compute the inverse. Under the hood, it uses advanced optimized algorithms to find the solution, and it can handle a wider range of problems than the direct inverse method. So, we have two views of the same problem: the procedural first principles algorithm of Gaussian elimination and the high-level abstract solution using the matrix inverse. Understanding both is the key. The first tells you how the machine computes, and the second tells you what it is conceptually solving. This foundation is essential for understanding everything from linear regression to the internal workings of deep neural networks. If you would like to see more examples, link for the blog post is in the description. If this detailed breakdown is valuable, hitting the like button tells YouTube to share it with more people. Subscribe for more deep dives into the mathematics of machine learning. In the next video, we will explore vectors and vector spaces. Thank you for watching.